Thanks to the organizers for organizing and inviting me to this beautiful workshop. So as you can see, the title of the talk is a lot of made-up words, but I'm going to define all of those words in just a short amount of time. So the talk is about high-dimensional data, and so this is something we have seen a lot, not only in this workshop, but over the last, I guess, decade. And so this is a setting where the data has a large number of variables. Large, both in an absolute sense and in a relative sense, relative to the number of observations you have of all the variables jointly. So this could range from gene expression data, where you have a large number of genes, to social networks, where you have a large number of users, to imaging data, where for 2D images, you have a large number of pixels. For 3D images, you have a large number of voxels. Right? So you have a large number of variables. So this is what I call big P data, because P is typically used to denote the number of variables in statistics. So when people say they don't know what big data means, well, big P, everybody knows what that means. Right? P is large. So that's what big P means. And over the last couple of decades, we know how to model, how to statistically model big P data. Right? So what we do is we impose structural constraints on the model. So these range from sparsity, group sparsity, and various structured sparse constraints, including low rank and various superposition structure, and so on and so forth. Right? And so this is what we do. And at some level of caricature, this proceeds in two stages. Right? So there is a statistical stage, and then there is a computational stage. So what's a statistical stage? So this involves formulating the statistical model, and then the structural constraints. These range from sparsity, group sparsity, and so on. And then devising the statistical estimation procedures. Okay? And so here the goal is statistical efficiency. You want statistical estimators that can learn the model, learn the statistical model in as few observations as possible. Okay? So that's statistical efficiency. And then you go to the computational stage, where you take the statistical estimator that has good statistical properties, and then you devise computational schemes, algorithms, that can solve these statistical estimation problems as computationally efficient as possible. Okay, so that's the computational stage. And so here, you're interested in the computational efficiency of your algorithm. Now, this actually has attracted a lot of attention, this computational stage, in recent years, where there are a lot of effort devoted to devising computational frameworks, including parallel and distributed computing frameworks, to solving these statistical estimators devised in the statistical stage as efficiently as possible. Okay? And what I would advocate instead is a comptastical approach. And so this is that word comptastical. It connotes fantastical, and so you have a nice, you automatically, it gets good connotations. So here, what I mean by comptastical is that you keep the computational and statistical constraints in mind right at the outset. Okay? And then you devise estimators to learn statistical models from data. As I mentioned, this two-stage approach is to some extent a caricature, where you first devise statistical estimators and then worry about the computational algorithms. Some amount of interaction already exists already. So for instance, in the statistical stage, if I say, if I imagine I impose some combinatorial constraints, I might say, for instance, I might say I want sparsity constraint least squares. Okay? So here, this is a non-convex optimization problem. And then I might say, in the computational stage, I might say, let's relax this to a convex problem. And so I essentially change the statistical estimator. And so I might go back to the statistical stage and revisit the statistical properties of my relaxed estimator. Right? And so this is something where there is an interaction between the statistical and computational stage, a feedback loop, if you will. Right? And recently, there have been a lot of proposals at taking into account comptastical approaches, if you will, of taking into account the statistical and computational constraints at the level of model selection, model and algorithm selection. So in other words, you do not worry about things at the estimator stage or the model stage, but if you have a family of models or if you have a family of algorithms, each of which have a particular statistical and computational efficiency. Then you can perform model or algorithm selection by taking into account your statistical and computational budget. Okay? And so there have been a lot of very interesting proposals. And so this is interesting, but the question is, can I do this kind of a computastical thinking right at the level of formulating the model as well as the estimator? Okay? So to do that, first let's revisit the computational stage. Okay? So I have devised my statistical estimation procedure, which has very good statistical guarantees. And then what does a computational stage entail? What do I do in the computational stage? Essentially, it's an optimization problem that I'm going to solve. Okay, so imagine that the statistical estimation problem is essentially requiring you to solve an optimization problem, constrained optimization problem typically. And I want to solve this optimization problem. And even when this optimization problem is convex, this is what happens. It's typically an iterative, the algorithms are typically iterative. Okay, so they proceed by running through multiple iterations. And the number of iterations typically depend on the accuracy to which you want to solve the optimization problem. If the accuracy is epsilon, then the number of iterations depend on how good the optimization objective function is. So if it's strongly convex, the number of iterations would typically be logarithmic in 1 over epsilon. But if it is, let's just say, not strongly convex, it's not curved everywhere, and it's only smooth, then the number of iterations could be as large as polynomial in 1 over epsilon, where epsilon is the desired accuracy. Okay? And so this is the number of iterations, and each iteration itself takes a finite number of steps, typically. And there is a lot of interest in iterative algorithms where each iteration does not take a large amount of time. Okay? So typically, each iteration only takes a finite number of steps. Okay? And so what are these steps? These are typically very simple operations. You might think about pointwise operations. I'm going to take a vector and threshold, perform some, apply some thresholding operator or some pointwise operator more broadly. Or I might take a matrix and a vector and multiply them. Right? Or I might try to solve linear systems or sparse linear systems. Or I might compute the inverse of a matrix. Right? So these are progressively more complicated steps. But typically, each iteration of an optimization algorithm only involve finitely many steps. Okay? And the number of iterations depend on the accuracy to which you need to solve the problem. Okay? Now, what's the problem with this? Typically, so once you fix epsilon, the number of iterations are also fixed. Right? The problem is that the number of iterations, even though they're fixed as a function of epsilon, could still be large. They could range from 100 to 500 and so on. Right? And the problem with this, so what's the problem? It's, let's say, 500 iterations of a simple optimization method. The problem is that the inputs to the later stage, was there a question? Yeah? Sure.
At this point, do you posit a relationship between desired accuracy and NNP, or at this point you not have a relationship in mind?
I do not have any relationship in mind. Think of this as an extraneous parameter. But typically, yes, you would want the epsilon to be dependent on the statistical accuracy of the problem. But I don't want to get into that. Right. So what's the problem with having many iterations? Well, one of the problems is that the input to the later iterations is not something you know a priori. Okay, so let's say I'm talking about the 501 first iteration. Right? So the input to that 501st iteration, I cannot predict a priori. If I knew that, I would start from that. Right? Whereas I might know the input to the very first iteration, especially if I make all these assumptions on the distribution of the data. Right? And so this is something that's a problem, because if I know the input and I know the set of steps that are involved in any iteration, I can profile that computation and I can optimize for that computation. Right? And so this is something I cannot do if I have an iterative algorithm. Okay? So that motivates asking this very simple question. Can I devise estimators that only involve computation amounting to one iteration of a typical optimization algorithm? In other words, they only involve a finite set of steps. That's it. So given this computational budget, what's the best you can do in terms of statistical guarantees? So that's the question we want to ask. And this is a very computastical question because you have the computational budget in mind right at the outset. Right? Now, so this is the question, and this is actually not a well-formed question, because what does a finite number of steps, what does this mean? Right? So what does each step mean? Because not all steps are made equal. Right? I'm going to talk about point-wise operations whose computational complexity would depend essentially on the dimensionality of the input. Or I'm going to talk about more complicated steps, such as solving linear systems, solving AX equal to B. Right? Now, this might take less time if A is sparse, for instance, and there's a lot of very interesting work from the theoretical computer science community on solving sparse linear systems very, very efficiently in time almost essentially quasi-linear in the number of non-zeros. But that said, it's a much more complicated operation than just performing point-wise operations. Right? And matrix vector multiplication, that's also more complex than point-wise operations. So not all steps are made equal, and it would be very interesting if we had some notion of effective work in mind. But I'm going to sidestep that. Okay? So that's a much more difficult enterprise, and I want to get towards that. But in today's talk, I'm going to ask a much simpler question, which is that given all these simple steps, matrix solving linear systems and thresholding and so on, so long as I give you a budget of finite number of steps, what's the best you can do? Okay? In part because I'm motivated by the fact that you can efficiently optimize. So if I know that I'm essentially only going to do matrix vector multiplications and point-wise thresholding, then I can optimize for matrix vector multiplications. Right? And in fact, we already have very, very highly efficient numerical linear algebra routines, just part of any OS and any a lot of compilers and so on. Right? And this is especially so if I know the distribution of the input. Okay, then I can optimize it even further. Okay? In fact, I can approximate the computation, and there's a lot of very interesting work in the applied math community where even solving linear systems, so solving least squares problems, if you know the distribution of the input, then you can actually approximate this very, very well for a lot of computational gain. Okay? So in other words, if I know the distribution of the input and know the steps, I can optimize these computations. Right? In fact, I can even implement it in hardware for all we know. Right? And so this is the question that we are asking. And I'm going to run through some, and this is what I call elementary estimators, which essentially involve a few or a finite number of very simple steps. I'm going to run through such elementary estimators, first for linear regression, high-dimensional linear regression, structured linear regression. Then I'm going to cover very briefly logistic regression. And in fact, we have methods for generalized linear models broadly, including Poisson regression and so on. And then I'm going to cover a little bit about elementary estimators for learning graphical models. Okay? So each of these is progressively more complicated class of statistical models, but we can still devise estimators that are elementary in the sense that I just described. Okay? So let's first run through the very simple class of linear regression models. Okay? So here, again, this is something a lot of people have brought up and something we all know and love. I have a real valued response y, which is essentially a linear combination of the signal that I care about, theta star, and with some noise added. Okay? So you do not observe the noise. What you do observe is the real valued response and the measurement vector x. And you see a few of these. And given this, you need to know the signal theta star. Okay? So this dates back to, I think, Gauss, the 500 years back. And estimators for this dates back to Gauss. And what people do is essentially solve a least squares objective, least squares problem. So here is everything collated into matrices and vectors. So y is the vector of responses, x is the matrix of measurement vectors, theta star is what I want, W is the additive Gaussian noise that I do not observe. Okay? And so this is an underdetermined linear system. And I want to solve this underdetermined linear system, obviously, by imposing some structural constraints on the signal. Right? So classically, as I mentioned, people have looked at this problem and have suggested finding the theta that minimizes this least squares objective. Okay? Find the theta such that x theta and y are close. And this actually has a closed form solution and is the solution of a linear system. Okay? So it's obtained by solving x transpose x times theta equals x transpose y. You solve that linear system, and the solution is what is known as the ordinary least squares estimator. Okay? So this is actually available to you in closed form. But it's only a valid estimator when the number of variables or the dimensionality of the signal theta, p, is smaller than n. Right? Because otherwise, this matrix x transpose x would not be invertible. So the linear system would be underdetermined, and it does not have a unique solution. So this is the caveat. But in the classical sampling regime, we have an elementary estimator for the linear regression problem. Right? So what do I do when p is greater than n? Well, what people have suggested is to solve regularized least squares instead, where the regularization would be suited to the particular structure that you have. Right? And so this could range from sparsity, group sparsity, low rank, and so on. Okay? So for instance, for the case of sparsity, the regularization we would all use is the L1 norm. Right? And so this regularized least squares actually dates back to the 50s, or possibly even before that, where the goal was to stabilize the least squares problem. By stability, I mean you change a few data points, the solution should not change too much. Right? So even in the setting where p is less than n, I might still want to stabilize my least square solution. So I might still want to regularize the problem. But here, regularization, obviously, as we all know, serves double duty. In addition to stabilization, it also encourages particular structure. Right? The caveat with this is that the typical optimization methods are iterative. Okay? And that's something we do not want. And there's a lot of literature on both the computational and statistical side of such regularized least squares problems. But we want to move to an elementary estimator instead. Okay? So let's revisit some of the classical elementary estimators. So we already looked at the OLS, which is solving this linear system. Right? And as I just mentioned, it's not well defined when p is greater than n. Right? Because the coefficient matrix of the linear system involves the sample covariance matrix, x transpose x, and that's not invertible. It's rank deficient. Okay? But there is a classical estimator that is well defined even in the high dimensional regime, and that's the ridge estimator. Okay? So that's L2 regularized least squares, and that's essentially solves this linear system instead. So instead of the sample covariance matrix, it's a sample covariance matrix plus some terms added to the diagonal of the sample covariance matrix. And then you solve the linear system. Okay? So it's x transpose x plus lambda I inverse x transpose y.
So here your model is that inverting the p by p matrix is easy.
Not necessarily. I'm just saying that these are the classical estimators. Right? But these are still, in some sense, you're absolutely right. Solving linear systems, dense linear systems, could still take time that's, in this case, order p cubed, right? Where p is the number of variables. But when the coefficient matrix is sparse, then you can solve these linear systems very efficiently. Or you can even approximate them even more efficiently. Yeah.
There's a more fundamental issue here, the issue of identifiability. Because when you have a large rank p, you could have lots of theta that give the same x theta value.
Right.
Result whose theta is not well defined.
That's right. That's right. That's right. So it's not consistent even, so typically in the settings where you impose structural constraints on the theta. So for instance, I might assume that the true theta is actually sparse or approximately sparse and so on. Okay, so there's even structured sparse and so on. Under all those conditions, there do exist consistent estimators, but this guy is not. Okay? And so that's the problem. There are other elementary estimators, such as correlation screening. So here what I do is something very simple. I'm just going to pick all those features, J, whose correlation with the response is larger than some threshold. Okay, so this is something very, very simple. And in fact, pretty much is something that almost everybody uses when they are saddled with, I don't know, 10 million features. Right? And I want to cull it down to something more manageable, like 1 million. There's actually been some analysis of this very simple procedure where they show that for consistency of this very simple procedure, you need to impose horrendously stringent conditions, as you might imagine, right? Because this does not take into account the correlation or the dependence among the features, right? So this is not something that obviously is a panacea, but at least it's in closed form and very simple, right? So let's step back and see what the state of the art is, right? So modern statistical estimators, at least in the convex regime, typically involve regularized MLEs. What do regularized MLEs do? The MLE part corresponds to goodness of fit to the data. Right? You find a theta that fits the data well. But as you pointed out, there is an identifiability issue, and so you actually also need to impose certain structural constraints for essentially identifiability, and that's also something that comes up in the regularized MLEs, and that's something that the regularization does. Okay, so this is what the typical estimators do. And as I mentioned, even though these are great, the optimization problems that these entail typically have to be solved by iterative procedures, and that's not something we want. Okay, so our approach is actually going to be very simple. We're going to start with the MLE, and we know that the MLE is good because it addresses goodness of fit to the data. But there's a couple of problems with the MLE. One, it's not suited to high-dimensional settings because of identifiability issues. And second, it does not satisfy the structural constraints I impose, such as sparsity. Okay? So what we're going to do is surgically modify the unmodified MLE so that it satisfies these two caveats, these two desiderata. Okay? So let's see how I'm going to do that for the very simple case of linear regression. Okay? So let's revisit our classical, well-known OLS estimator, okay? Which is solving this linear system, x transpose x and x transpose y. Okay? So what is the problem with this? The coefficient of the linear system, coefficient matrix of the linear system, was the sample covariance matrix x transpose x by n, right? And this is rank deficient. And so I cannot solve this linear system with the sample covariance matrix in the high-dimensional regime where p is larger than n. So what do I do? Okay? So what modification can I possibly make to the OLS estimator so that this becomes well-defined in the high-dimensional regime? Okay? In general, this is a difficult question to answer. But what if I actually give you additional bits of information? Okay? What if I tell you that the population covariance matrix of x, okay, what if the population covariance matrix of x satisfies some conditions? Oh. So satisfies some conditions. Okay? Then you might be able to leverage these conditions to get estimators that are available in closed form. So let's look at what some of these conditions might be. Imagine that the population covariance matrix is approximately sparse. Not exactly so, but approximately so. What does that mean? Each row of the population covariance matrix has an LQ quasi-norm bounded by some constant, okay? Where Q ranges from 0 to 1. If Q is 0, this is exactly Hart sparsity, where I say that every row of the population covariance matrix has bounded number of non-zeros. But for Q greater than 0 but less than 1, this amounts to some weak sparsity. Okay? So the Toeplitz matrix, defined as so, does not have any zeros, but it's still, I would call it, approximately sparse. Okay? So if the population covariance matrix, I know, satisfies this property, then I can modify the sample covariance matrix which is not consistent in various operator norms to something that's not only consistent but has better properties. Okay, so one thing I could do is just threshold the sample covariance matrix entries. Okay, sigma hat n is the sample covariance matrix, and I'm just going to apply some thresholding operator which satisfies some properties. It could range from the soft thresholding operator or the hard thresholding operator or various other operators. Okay, that's it. But what if my population covariance matrix is not weakly sparse? Right? So then what could I do? Perhaps it's diagonally dominant. What does that mean? The diagonal entries along any row are larger than the rest of the off-diagonal entries along that row. Okay? So this is known as diagonal dominance. In case your population matrix is diagonally dominant, you could modify your sample covariance matrix estimate using this very simple procedure where you threshold the off-diagonal entries just as previously done, but I'm going to add elements to the diagonal just as you did in the ridge estimator. Okay? So what we show is that under both of these conditions, if the population covariance matrix does satisfy either of those two properties, the two estimators that we just defined satisfy some very nice properties. Okay? For this nu was a property of the thresholding operator, and this nu does not need to be very large. Scaling a square root log p by n, our covariance matrix estimate is invertible and is very close, still very close to the sample covariance matrix. Okay, so I'm not modifying the sample covariance matrix too much, close in some operator norm, that's important, and yet is invertible. Right. Oh yeah, so this is a well-known, so learning sparse covariance matrices, so even Bickel and Lavina had various estimators of sparse covariance. Pretty much. But we generalize this to other settings such as diagonal dominance and so on. Okay? So if you have a good covariance matrix estimate, you should use it. Okay? So the lesson, or really the crux of our analysis, comes here. Okay? So what we say is to take the OLS estimate, and instead of the sample covariance matrix, you plug in a better covariance matrix estimate. Okay? That's suited to the conditions in a population covariance matrix, and then just perform essentially this OLS surrogate. Okay? So this is very simple. You're now performing a linear system, solving a linear system with this matrix sigma twiddle. But now this is actually better than the OLS linear system because the sigma twiddle is actually sparse. Okay? So you're solving a sparse linear system, which you can do very, very efficiently. But there is still one caveat with this, which is that this is not structurally constrained. This estimator is not going to be structurally constrained. Right? In fact, I didn't even bring up the structural constraint on the original signal. Right? It could be low rank, it could be sparse, group sparse, and so on. This guy is not going to have those structural constraints. So where do we impose the structural constraints? What I'm going to do is embed this even further into an optimization problem. I'm going to find a theta that is going to have minimal structural complexity such that it's not far from that OLS surrogate that I mentioned before. Okay? So this is very similar to Danzig and even stuff that we essentially do with regularized MLEs. But the interesting thing is that for a large class of regularization norms, this is actually available in closed form. Okay? I guess I just have, okay. So this is available in closed form. For the case of sparsity, this is the estimator. I essentially perform an additional level of thresholding. So I guess I have just 1 minute, perhaps 0 minutes. Okay, so I just want to say that the rates are comparable to that of the lasso. And surprisingly, for the cases where, so let me just look at the ROC plots. For the cases where the population covariance matrix actually satisfies the properties that I just mentioned previously, our estimate actually beats the lasso. And moreover, is much, much faster than some of the fastest implementations of lasso. Okay, so a much simpler estimator, just by leveraging additional information, is actually much better. So I won't have time to go into the rest, so let me just summarize. our estimators are motivated by what I call comptastical estimation, where you take into account the computational and statistical constraints right at the outset. Okay? And essentially, these estimators only involve a few simple steps. Okay? These simple steps involve solving sparse linear systems, and you might say, hey, that's a complicated problem. Right? But there is a lot of recent research on doing so efficiently, and what I would argue is that there can be even further research on solving those even more efficiently, given that there are these wonderful estimators that all they require is solving a sparse linear system. Okay, thanks.